Hello students. We continue our discussion on rational functions with a focus on graphing them. Put each rational function in factored form, give the domain, simplify if possible, then graph the function by hand. Confirm with technology. So this first one, f of x equals x squared over 2. This is already in factored form. So this technically is a polynomial as well as being a rational function. It can be thought of as simply 1/2 of x squared, which I see that as a transformation of our parent function. If you were to make a small table of points, plug in 0, you get 0. Plug in 1, you get 1/2. Plug in 2, you get a square 2, you get 4, and then do half of that, so you get 2. Plug in -1, you'll also get positive 1/2. And plug in -2, you also get positive 2. So we have 0, 0. We have 1, 1/2, 2, 2. So -1, 1/2, and -2, 2, etc. It's a slightly flattened parabola. And this says to confirm with technology. Here's our flattened parabola. Okay, the next one looks a lot more complicated. But watch what happens when you factor it. In the numerator, I can factor out an x squared. That leaves an x minus 1. In the denominator, I can factor out a 2. That leaves an x minus 1. And then I can cancel some x minus 1s. But before we do the simplifying, we have to give a domain. And the domain is that x can't be 1. So in this function g, right, you cannot plug 1 into this function g. And so let's be clear that this is the domain of g by doing the following. I'm going to say domain sub g. Now, if you simplify this back down to x squared over 2, after canceling the x minus 1s, you technically create a new function that no longer has a domain restriction. So let's call this g tilde of x. It's not g of x really anymore. It's a new function because its domain is all real numbers. And in order to graph g, we can just graph g tilde. But then we have to remember that g has a domain restriction. And since g tilde is the exact same thing as our function f over here, then we should expect to get the same image. Well, this is a graph of g tilde. But if I want to give a graph of g, then I have to have a domain restriction, which means x can't be 1. So you would go to where x was 1 and put a missing point where there used to be a solid point. So it looks more like this. We have a domain restriction, a missing point at 1, 1/2. And this is the graph of g. It's the same thing as a graph of f, but with a missing point. Let's go to Desmos, hide f, and reveal g. And it looks like the entire parabola is there. But when you trace on this, notice that when you go above 1, Desmos is revealing that the function is undefined. It puts a hollow point there, but you wouldn't see it otherwise. So what looks like a continuous function actually has a discontinuity in it. There's a break in the graph, a missing point at 1, 1/2. So when you make your drawing by hand, it's better to make it like this and make that point obvious that it's missing. The next function, h, looks even more chaotic, but watch what happens when you put this in factored form. So I can begin by factoring out x squared of the top. That leaves me x squared plus x minus 2. And the bottom I can factor out a 2. That leaves me x squared plus x minus 2. Now notice those are identical and can cancel. But I'm going to keep factoring anyway. That's going to be x plus 2 times x minus 1 over the same thing, because this helps me get the domain restriction. So we know the domain of the function h, x cannot be 1 or -2, because you're going to get a 0 down here. But if you do the simplification and you cancel all 4 of these things, then technically we've changed it to a new function. We're going to call it h tilde. H tilde is x squared over 2 after you do the simplifying, and the domain of h tilde is all real numbers. So we technically have a different function. If I'm going to graph h, the original, then I can really just graph h tilde, but then remember to remove 2 points, have 2 domain restrictions instead. So we're going to have a missing point at 1, 1/2 and at -2, 2. Those are where the points used to be, and this is a graph of h. 2 missing points. If I started with this and I said, hey, where are the missing points? Then what you would want to do is simplify h down to h tilde, graph that, but then remember these 2 domain restrictions, and to figure out the y coordinates, you simply have to plug these domain restrictions one at a time into the simplified version, into h tilde. And that will tell you where these hollow points should be. If I hide g and reveal h, it looks exactly like the others did, except when you do a trace, you're going to notice that we have 2 problematic areas. So we have one there, one undefined, and then the other one's going to be -2, undefined. So there are 2 missing points. By the way, if you want to force your graph to show the missing point permanently, then go ahead and insert a line and put that point in there. For example, put in -2, 2. And then go to the settings and just make it a hollow point instead, make it green, check the label box, and you can force the presence of the hollow point in your image using the technology. Desmos doesn't automatically put in those missing points for you to see. You have to hunt for them. I just want you to realize, if I wanted to take this graph right here and poke a few holes in it, if I wanted to remove the point 1, 1/2, then I would take the rule for this graph, which is x squared over 2, but then multiply it by x minus 1 over itself. And when I do that, I effectively take the graph of x squared over 2 and create a domain restriction. Multiplying by x minus 1 over x minus 1 removes the point when x was 1. And if I want to remove 2 points, remove this point and this point, so start with x squared over 2, which is the parabola, and remove a point when x is negative 2, and remove a point when x is 1. And so in theory, you could just keep this up and remove dozens of points from a graph if you'd like. Okay, now we go to the next slide. The set of instructions you see here are going to be repeated for the next several tasks. We're just going to get practice graphing these rational functions, finding their asymptotes, and connecting the dots, and answering a few questions. Well, I'm going to begin by putting this in factored form. Factor a 2 out of the numerator, and the denominator factors to x minus 4 times x plus 1. Notice this one, there is no simplification that happens. I'm going to call this one here our expanded form, and this one here our factored form. Now the two forms are useful for different reasons. So let's begin with question A, find the domain. The domain, I'm going to use factored form and look to that denominator and tell me what all the x's can and can't be. So part A, the domain is that x can't be 4 or negative 1. Question B, find all the intercepts. Let's start with the y-intercept. The y-intercept you find by just plugging in 0 for x, if you're allowed. In this case, if you plug in 0 for x, I'm going to use this form to do it. So plug in 0 for x, that goes away, we get negative 4 in the top. And plug in 0 for x, those will go to 0, getting you negative 4 on the bottom as well, so we get positive 1. So we know that point 0, 1 is our y-intercept. Now for the x-intercepts, you change the function to 0, and you solve this equation. You set the whole function equal to 0, and I'm going to use the factored form. You can now multiply this to the 0 side, which is just going to 0 it out. So this really just translates into 0 equal the numerator, and then solve for x. We get x equals 2. So we know an x-intercept is 2, 0. So we can start plotting some points here. There's 2, 0, here's 0, 1. If necessary, you'll notice I left the scales off. So if you want that to be 0, 10, you can. Part C, find all the asymptotes. Let's begin with the vertical asymptotes. Those are connected to the domain. Every domain restriction you have is potential for a vertical asymptote. When you try to plug in 4 into this, do you get 0 over 0 or non-zero over 0? And the answer is we get non-zero over 0. That means we have a vertical asymptote at 4. If you plug negative 1 into this function, either there or there, doesn't matter, you're going to get non-zero over 0. That means vertical asymptote. So we have vertical asymptotes will be x equals 4 and x equals negative 1. So now that I'm seeing x equals 4, I'm going to want to change my scale just so I can see everything in my image. So that's going to be 2. This is going to be x equals 4. And as long as you label things, then things will be clear. The other one was x equals negative 1. So now we have to look for either a horizontal, a slant, or a non-linear. And I should tell you, we're not going to do any graphs with non-linear asymptotes. But let's look for slant versus horizontal. And we can do that by comparing the degrees. So the expanded form is very useful for this. This is a first degree, x to the 1 up there, divided by a second degree. This means this is bottom heavy. And as we did in the last lecture, bottom heavy implies that y equals 0 will be a horizontal asymptote. Y equals 0 is the x-axis. And notice we have an intersection with the horizontal asymptote, but that's okay. It's the vertical asymptotes that should never be intersected. Let's get item D. Find any intersections with the asymptotes. Okay, well there's already one here, and you'll never find intersections with the verticals. Well, because the horizontal asymptote is the x-axis, we've already found x-intercepts, and there's only one. So the only point of intersection with an asymptote is at 2, 0. So at 2, 0, the graph intersects the horizontal asymptote. Item E. Find any missing points. And by missing points, we're talking about the points like up here where you might have a point that was removed. And in this case, because we did not get any cancellation of factors, there will be no missing points. So we'll say for part E that there's none. Graph by hand. So we're on F, we'll just do that over here, and then G is confirmed with technology. Here are the options. You have an asymptote. It only gets intersected right there, the horizontal asymptote. And your vertical asymptote, you can imagine that your graph would be continuous, but for the vertical asymptotes that sort of cut it. So there's going to be a piece here, and a piece here. And your options for over here, if there's a horizontal asymptote, then you know the graph going that way is going to follow it either from above or from below. And if you're not sure which, then you can plot some extra points. Let's plug in an x-coordinate that's left of that asymptote. So maybe this x-coordinate right there, which is negative 2. And plug in negative 2 in for x. And I'm going to use the factored form to do my mental work here. Negative 2 minus 2 is negative 4 times 2 is negative 8. And then the bottom becomes 6. So we have negative 8 over 6. We have a negative number when all is said and done. Negative 8, 6, which is negative 4/3. So if we go left 2, we have to go down 4/3. So there's a point down here somewhere. Keep in mind my vertical and my horizontal are not on the same scale. This right here is the point, or 0, 1, and this is the point 2, 0. But as soon as I put that point right there, then I know that my piece has to follow an asymptote, hit this point, and then follow this asymptote down. I know it can't somehow turn around and follow this asymptote up, because then it will cross the x-axis again, and I know there are no more x-intercepts. So this sort of forces the entire portion of this graph to be down here in the third quadrant. And as you zoom out, you should expect to see following the asymptotes. Okay, the other piece, I'm going to connect these right away. Now, the same thing that we used for polynomials to know if I should bounce off the x-axis or cross it, apply here. So notice that this x minus 2 factor gave us the 2 x-intercept. And there's a 1 here. That makes it an odd multiplicity, so you expect the graph to cross the x-axis, to have a change in sign and y-coordinate when you go across x equals 2. And therefore, I know that it has to cross and enter into the fourth quadrant like this. Now from there, I have one of two choices. Turn around and go up, but if I do that, I'll cross the x-axis. Can't do that. So it's going to have to continue on its way down. It's the only really option. Now over here, I could make this turn around and go down with this asymptote, but again, you're going to cross the x-axis, and there are no more x-intercepts. So the only real option is to go up with it. And the last piece, pick something larger than 4, like 5. So I'm going to plug 5 into this version right here. So let's do 5 minus 2 is 3 times 2 is 6. And the bottom's going to be also 6. So I believe I get a 1 out of this. This is the 0.51 right there. That tells me that I know I can't be down here. It has to be up like this one. Also keep in mind that you're making a function. So you wouldn't want graphing both pieces, because then you would fail the vertical line test. And this becomes the graph of our function. I want to point out one more thing. This has to do with whether or not surrounding an asymptote, let's say this is an asymptote, it's possible that the graph goes up with the asymptote on both sides or goes down with the asymptote on both sides. The other possibilities are what you're seeing in this particular example, that surrounding this asymptote, one side of it is going down, the other side is up. Surrounding this asymptote, one side is down, the other is up. The way to know that you're going to get opposite direction or same direction behavior around the vertical asymptotes is to look at the multiplicity of the factors in the denominator. So look at this x minus 4. This is why we have a vertical asymptote at 4. And it has a 1 power. When you have an odd multiplicity on that factor, then your graph will go in opposite directions around that vertical asymptote. But the multiplicity on this factor is also 1. So we have odd multiplicities on both those factors, which means surrounding each asymptote, I expect opposite behavior, one side to go up, one to go down. Opposite behavior, one side to go up, one side to go down. And if I knew that this side going down, the odd multiplicity at x equals 4 tells me that side had to go up. So I never needed to find this extra point. I'm going to try to use that knowledge moving forward to speed up our ability to graph. And then the last part was confirm with technology. So I'm going to just go over here and reveal the graph that we just did. I don't have any asymptotes plotted in here, but you could insert them. And then the horizontal was y is equal to 0. So here's our 3 asymptotes, 2 vertical, 1 horizontal. Okay, next one. First step, put this in factored form. So I'm going to begin by factoring out an x. From the top, that leaves x minus 5. At the bottom, you can factor out an x, but I don't like the fact that the leading term is not written first. So it could be helpful to write this as negative x cubed plus 9x. And then if your leading coefficient is negative, I like to factor out a negative as well. So I'm going to factor out a negative x. That leaves an x squared minus 9, which factors itself to x minus 3x plus 3. Notice there's a similar factor that's going to cancel. But before you do canceling of those factors, you need to do your domain. Part A, the domain of this function g is that x can't be 0, can't be 3, can't be negative 3. Now, when I cancel these x's, I'm actually going to create a g tilde, which is really what we want to graph here. But then remember that we have to have a restriction at 0. Well, let's move forward. Let's just go to find all intercepts. So for part B, let's do g of 0. G of 0 does not exist, so there is no y-intercept, because 0 is not in our domain. Of course, if you cancel these x's, you can plug 0 into g tilde. You can't plug it into g. To find the x-intercepts, you set equal to 0 the numerator. So you would get x equals 0 and 5, but 0 is not in domain. So we only have one x-intercept, 5, 0. I'm going to go ahead and write the g tilde version. So if you simplify this, it would look like x minus 5 over negative x minus 3 times x plus 3. You know, this here is still g, but this one here is the one we're calling g tilde. It's a new function. And this is really what we're going to be graphing, but then we're going to remember this extra domain restriction and put a missing point in our graph. Now we're going on to item C, which is find all asymptotes. You can look at the original. It is second degree divided by a third degree. So it's bottom heavy. Bottom heavy, it tells us a horizontal asymptote is y equals 0. That's a horizontal asymptote. And for the vertical asymptotes, those are the values of x in our domain that didn't have canceling factors. Our vertical asymptotes will always be a subset of our domain restrictions. And it's only going to be these two, because 0 is a domain restriction, but it corresponded to a canceling factor. So in our simplified version, 3 and negative 3 are the only values of x that will cause non-zero divided by 0. And so those are going to be the only two vertical asymptotes. Let's go to item D next. Find any intersections with asymptotes. Well, only possible intersections will be with the horizontal, and since the horizontal asymptote is y equals 0, it's the x-axis, then our x-intercept is the only intersection. G intersects the horizontal asymptote only at the point 5, 0. Item E, find any missing points. Okay, so we do have a missing point when x is 0, so we got to plug 0 into G tilde. Plug it into that thing right here. We get -5 up top, we get +9 on the bottom, so -5/9. So we're going to have a missing point at 0, -5/9. And we are ready to start plotting. I'm just going to do a scale where horizontally each block will be 3, so this will be a gap of 3. Okay, so here's my x equals 3 and x equals -3. As long as you label them, then it's clear that you're using a different scale here. Y equals 0 was the horizontal asymptote. There was no y-intercept, but we had an x-intercept at 5, 0. And this is all we have to go on, except we know that there's a missing point at 0, -5/9. Well, let's put -5/9 approximately here. So we do have this missing point and no other x-intercepts. So I have a piece, and a piece. There's 3 pieces I got to focus on, and I'm going to focus first on in between the vertical asymptotes, because our graph does have to hit this hollow point. From the hollow point, what do? Well, can I go up with an asymptote? No, because it's going to hit the x-axis. There's no other x-intercepts. So it has to go down on this side. Same thing's true on this side. Okay, let's use our multiplicities. Notice that the multiplicities on both of these factors are 1, and the multiplicity on our x-intercept is also 1. So we're going to cross the x-axis at the x-intercept, and at each asymptote, our graph will go in opposite directions. So let's focus on this asymptote first. If one side of that asymptote is going down, then the other side is going up, and then we have another asymptote. So it's going to have to be something like this. Okay, now let's focus on this asymptote. At x equals 3, the multiplicity was 1, therefore we have opposite directions. So if this side of x equals 3 is going down, then the other side, it has to be going up. And then we have an x-intercept to hit. Do I cross or bounce off? Well, I must cross, because the multiplicity on the x minus 5 up here is also odd. So we're going to cross the x-axis, which means I'm going to have to turn around and then follow the asymptote that way. So there's going to be sort of this little dip down here. I think we are now ready to do this with technology. So here's the next one. Let's move our asymptotes to where they belong. 3 was one of the verticals. The other vertical was -3. The horizontal was 0 again. And notice that we have a shape. If I trace this, you're going to see that there's going to be a missing point right there at 0, -5/9. So we do have 3 domain restrictions. 2 are vertical asymptotes and 1 is a missing point. And let's change my horizontal scale and then my vertical scale just so you can see that dip. I'm trying to exaggerate the presence of this dip here. So you notice that we do go through the x-axis at x equals 5. It dips below the x-axis, and then it turns around and then follows the asymptote off that direction. Let me hit the home button. I meant to show you this earlier. One thing's true about these graphs and asymptotes is when you zoom out, the graph really just starts to look like the asymptotes. That's what I mean by saying that an asymptote guides the graph as you go away from the heart of the graph. And go to the next one. Let's get this into factored form again. Again, I'm going to factor out the negative, so it's x squared minus 4, and then factor that. So it's x minus 2, x plus 2. The bottom, it just factors to x minus 1 squared. And let's do domain. Domain of the function h is that x cannot be 1. Let's go now to the intercepts. Part B, let's do the y-intercept. Let's do h of 0, plug that 0 in for h. We get 4 up top and we get 1 down below, so we get 0, 4 is 1 point. And now let's set the numerator equal to 0. Solve for x, and we get 2 x-intercepts, 2, 0, and -2, 0. Number C, vertical asymptotes. There's only one domain restriction, x equals 1. Is it a missing point or a vertical asymptote? Well, if you try to plug 1 into this, you're going to get non-zero over 0. That means vertical asymptote. Notice that this is a second degree divided by a second degree. This is balanced. So you have to divide the leading coefficients. So -1 over 1. We talked about this in the last lecture. So we get y equals -1 over 1, which is just -1, and this is your horizontal asymptote. D, find any intersections with asymptotes. So now we have to say, where does this function hit this asymptote? So we have to now solve an equation. We do this by setting the asymptote equal to the function. And I'm going to use the expanded form of the function, and then solve this equation for x to see if we have any points of intersection with this asymptote. Well, if I multiply both sides by this denominator, so I'm going to multiply this denominator to this side, that gives me -x squared plus 2x minus 1 has to be equal to 4 minus x squared. Now add x squared to both sides, they cancel. Add 1 to both sides, we get 2x equals 5. Now divide, we get x equals 5 halves. H intersects the horizontal asymptote at, and the x is 5 halves, and of course the y is -1. Part E, find any missing points. Well, no factors here canceled. There's not going to be any missing points we have to worry about, so that's done. And then F is graphed by hand. Now I got my intercepts plotted. I got my one vertical asymptote. I got my one horizontal asymptote. I can see that we're going to intersect the horizontal asymptote at 5 halves, -1, so that's 2.5 -1. So right here is going to be an intersection with the asymptote. Okay, there's going to be one piece, two pieces on either side of that vertical asymptote. Obviously, we're going to have to connect some points here, so I'm just going to do that. And then from here, I can either turn around and go down, but that would cause another x-intercept and another intersection with the horizontal asymptote. So it can't turn around and go down. It's got to keep going up. Over here, we're going to have to certainly be cross the x-axis, because notice that the multiplicities on the two x-intercepts are 1 and 1. So we expect crossing and crossing, which is what you wanted to do anyway, because if it bounced off, then how would it get back to this asymptote without crossing the x-axis again? You kind of expect it to cross just so it can follow the asymptote. Now, on the other side, I think it's pretty clear that we've got this sort of behavior happening. At this x-intercept, we have an odd multiplicity, so we have to cross the x-axis. Don't expect it to turn around, because then we're going to cross. So it's got to keep going up. And then over here, we expect a crossing of the y of the asymptote and then a following from the other side. Now notice that this vertical asymptote came from this x minus 1 squared. Even multiplicity. When there's an even multiplicity on a factor that's causing a vertical asymptote, you expect the graph to go in the same direction surrounding that vertical asymptote. So both ends going up. And that's exactly what's happening here. Now let's go over to technology and graph this one. Let's move our vertical asymptote to x equals 1. Hide the other one. We don't need that one. And the horizontal asymptote was y equals -1. And notice what's going on here. We do have it crossing the horizontal asymptote and then following it from beneath it. And over here we have it following the horizontal asymptote above it. Confirming our image here. Let's go to the next one. Factored form is our first goal. I factor a 2 out. That leaves x squared minus 4x plus 4, which factors to x minus 2 times another x minus 2. But the bottom is prime. The sum of squares does not factor unless you use imaginary numbers, which we're not doing. So this is the only factoring that we can do. Let's find the domain. When you set the denominator equal to 0, x squared plus 1 is always 1 or higher. The denominator can never be 0, so our domain is all real numbers. This is going to have no vertical asymptotes. Part B, the intercepts. Let's do the y-intercept first, p of 0. Plug 0 into p, and I'm looking at the expanded form to do this. So we get 8 up top and 1 on the bottom, so we just get 8. The x-intercepts, set the numerator equal to 0, and we get one answer, 2. So 2 comma 0 is the x-intercept, and up here we concluded that 0, 8 was the y-intercept. Part C, find all asymptotes. All right, well, there's no vertical asymptote because our denominator can never be 0. So we just want to look for a horizontal or slant. So here's where we look to the degrees. This is a balanced, again, x squared over x squared. So divide the leading coefficients, 2 and 1. Balanced, this tells us that y equals leading coefficient over leading coefficient, which is going to be just 2, is our horizontal asymptote. Find intersections with the asymptotes. All right, so this is where we have to do a little bit of work. So I'm going to take the horizontal asymptote, which is 2, and set it equal to the function. And then we're going to solve this equation for x. I'm going to begin this by multiplying just that to this side over here. So that gives me 2x squared plus 2 is equal to 2x squared minus 8x plus 8. The 2x squares will cancel each other. I'm going to add 8x to this side and subtract 2 to the other side and then divide. So we get 3/4. So we know that the graph of P intersects the horizontal asymptote at the point 3/4 comma 2. Any missing points? Well, no factors canceled here, so there are no missing points. Looking at our data, I might want to do a different vertical scale. Let's do vertically each thing is 4. So this would be 0, 8. But horizontally, let's go with our normal 1 unit. So there's 2, 0 right there. No vertical asymptotes. We have a horizontal asymptote at 2. The point of intersection with the intercept, 3/4 comma 2. So we're actually going to intersect this at this point right here. Obviously, we have something like this going on. At this x-intercept, do I cross and then come back to this asymptote? But that would force another x-intercept, so it's going to bounce off and follow. And we know it's going to bounce off and follow because at 2, look over here, x-intercept of 2 came from this factor, which has an even multiplicity, so we bounce off the x-axis. Over here, we're going to have to eventually turn around and follow this asymptote this way. No more intersections with the asymptote. So this one here, we get an image like this. So let's go ahead and confirm with technology. And here's what it actually looks like with a more consistent scale. Change the scale, we get something that looks more like what I drew. Okay, next one. Do the following for the rational function. Find the domain. Let's first put this in factored form. The top factors to x minus 4 times x plus 3. The bottom is already x plus 3. Oh, that's interesting. Okay, so we are going to get cancellation of factors. So there will be a missing point in here. Write down the simplified version is just x minus 4. This one here is still q function, but this one here is q tilde. It's the simplified version. Really what we're graphing here is the simplified version. The simplified version is just x minus 4. Every block vertically and horizontally is 2. So x minus 4 has a y-intercept of -4 and a slope of 1. So our graph is just that line. But we did have a domain restriction, right? The domain of q, not the domain of q tilde. The domain of Q is that x cannot be -3. That domain has to be reflected in this graph here. There's -3 right there. On this line, we're going to have a missing point that's going to occur right there and then continue that line that way. The question is, what is its y-coordinate? Intercepts. We can see a y-intercept clearly of 0, -4 and an x-intercept at 4, 0. Asymptotes. There are none. There's no horizontal and no vertical and no slant. Graph any missing points. The only missing point occurs when x is -3. Oh, also part D we didn't have to do because there were no asymptotes. Now part E, Q tilde of -3 is equal to -7. That's what this missing point is. We've already graphed it by hand. Now we just have to confirm with technology. You will notice that by the time we try to get to -3, comma undefined, there's a missing point. Let's go to the next one. Okay, factoring this one here, the top factors x -4 times x plus 3, and this time over an x plus 1. So this time we don't get any cancellation. So there's not going to be any missing points. The domain of this w function is x can't be -1. Find all intercepts. Let's do w of 0 to find the y-intercept. Plug in 0, I get -12 up top and +1 on the bottom, so we just get -12. And then set the numerator equal to 0, and we get two x-intercepts, 4, 0 and -3, 0. Part C, find all asymptotes. This one has a vertical asymptote at -1. If you try to plug -1 into this, you're going to get non-zero over 0. Now for the horizontal and or slant. Notice that this one's now top heavy, x squared over x. It's top heavy by 1 degree. From our last lecture, that means that we have a slant asymptote. And the way to do it is we just do long division and we keep the quotient. This was all covered in the last lecture. So we know that top heavy by 1. That tells me that there is a slant asymptote. Notice we're dividing by x plus 1. So that means I could use synthetic division as well here. I could put -1 in the corner and then put the coefficients of the dividend. Bring the 1 down, multiply, add, and there's our remainder and here's our quotient. So the quotient is what winds up being the slant asymptote. So y equals, this is 1x minus 2. X minus 2 is the slant asymptote. Find any intersections with the slant asymptotes. So we have to set the function equal to the slant asymptote. Here's our slant asymptote equal to the original function. We're going to begin by multiplying this denominator to that side there and then foiling. So that's going to give me x squared minus x minus 2 is equal to x squared minus x minus 12. And notice that all the x's cancel, leaving minus 2 equals -12. This is no solution. So in other words, there's no point of intersection with this slant asymptote. E, no missing points because there's no canceling factors right there. And now all we have to do is graph by hand. I'm going to certainly do some different scales here. Okay, we have a vertical at x equals -1. I'm going to put -1 right here. So horizontally, each block will be 2 units. And that's the only vertical. Okay, so I don't need the other one. This other one I want to turn into a slant asymptote. Let's get it correctly positioned. The slant asymptote is y equals x minus 2. So it needs to cross the x-axis at -2 and have a slope of 1. Now I'm going to change my vertical scale because I have to get 0, -12, the y-intercept in here. I'm not going to think too hard about what the vertical scale is, but let's just say 0, -12 is down here somewhere. 4, 0 is right there, and -3, 0 is right there. So these are our intercepts. Well, it seems pretty clear. We've got an asymptote, a point we're going to cross and follow an asymptote. Do I cross the x-axis at 4? The answer is yes, because the power on that x minus 4 is a 1. Same thing for here. And an implied 1 on that one too. So we've got multiplicities that are odd all across the board. So I expect a crossing of the x-axis. I expect a crossing of the x-axis at that other one. Follow the asymptotes. Notice surrounding the vertical asymptote, the graph goes in opposite directions. This looks just about right. Let's go ahead and confirm. And let's go ahead and type in that asymptote. We're going to graph the line x minus 2. Zoom out, you can see our intercepts are all correct. When we zoom out, it looks like just a big X because we're just following a slant asymptote and a vertical asymptote. Oh, also I forgot to graph my vertical asymptote. X equals -1. Let's go to the next one. Here's a very big looking function that it's already factored for us, so that's great. So we can look at the domain right away. The domain of this function v is x can't be 3, -2, or -1. Part B, find all intercepts. Well, the y-intercept. Plugging in 0 for x, I get 3 in the top because I get 3 times 1 times 1. Don't forget that square. Plugging 0 into the bottom, I get 9 times 2 times 1, so I get 18. And 3/18 is the same as 1/6. Well, notice we do have a cancellation of x plus 1 over x plus 1, so we do get to simplify this to a v tilde. Set that numerator equal to 0 and solve for x. So we say 0 is equal to x plus 3 times x minus 1 squared. That gives me two answers, 1 and -3. The asymptotes. Now it's very important to see that if you were to FOIL v, it's not written in expanded form, but if you were to do that, if you were to just focus on the leading terms, you would get an x to the 4th leading term, and then plus a bunch of other stuff. But the bottom would be the same. So because of this balanced, we know that y equals 1 is a horizontal asymptote. Just divide the leading coefficients. And the vertical asymptote. Vertical asymptotes will be precisely those values of x from our domain restriction, and I should say x can't be, but the canceling factor of x plus 1 leads to only 2 domain restrictions that will cause a non-zero to be divided by a 0, which is what will cause the vertical asymptote. So vertical asymptotes are going to be x equals 3 and x equals negative 2. D, find any missing points. We definitely had a missing point. Into v tilde, I'm going to plug in negative 1, that's a domain restriction, but plug it into here and see what y coordinate we get. And negative 1, plug it in there, we get an 8 up top. Into the denominator, I get 16. That's going to give me a 1/2. So that's a missing point. Graph by hand is what comes next. Okay, we have a horizontal at y equals 1. We have a vertical asymptote at x equals 3, which I'm saying is right here. Another one at negative 2, which I'm saying is right there. Y-intercept 0, 1, 6, so just above the origin. 1, 0, and negative 3, 0. So I didn't worry about whether or not we're going to intersect the horizontal asymptote this time. The missing point, let's put that in there too. Negative 1, a half. Well, half is more than a 6, so it's roughly in here. Obviously, we're going to connect these. Do I cross the x-axis or bounce off it at 1? Well, look to this factor here, even power. That means we're going to bounce off at 1. So we're going to have to bounce off and go up. Which means, do I turn around and go back down? No, but then you'll cross the x-axis again, and there are no other x-intercepts. So it's got to keep going up. It's going to force it to cross the horizontal and go up with this vertical. Over on this side, do I turn around and go down? No, because it'll cross the x-axis. There are no other x-intercepts. So it's got to continue to go up. Okay, now let's use the multiplicities of the denominator to help with the vertical asymptotes. Let's focus on this asymptote first. At x equals negative 2. Negative 2 came from this factor right here, which has an odd power on it. There's an implied 1 right there. So it's an odd multiplicity. So I expect around this asymptote the graph to go in opposite directions. So if it's going up on this side, then I have to go down on the other side. And then do I cross the x-axis? Yes, because we have an odd multiplicity on the x plus 3. So we cross that negative 3, which is good because I have to get to that horizontal asymptote somehow, and it's going to have to follow it this way. And in the other piece, surrounding x equals 3, so surrounding this asymptote, look to the factored form. Notice the even power on it, so even multiplicity, so the graph needs to go in the same direction. So if it's going up on one side, it needs to be going up on the other side. And then we have a horizontal asymptote to follow, and maybe even cross. Notice I didn't study to see if I would cross the horizontal asymptote some more, but this is a basic feel of this graph. Y is equal to 1 was a horizontal. The two verticals were at x equals 3 and x equals negative 2. And we have this image. Now this is clearing up a few things for us, so we don't see crossing of the horizontal asymptote other than the middle piece crosses the horizontal asymptote twice. But the other piece that we're looking for here is the missing point. So let me just do a quick trace here and show you that we do have that missing point. There is a missing point at negative 1, a half. Okay, we're ready for the last slide. You must design a box with no top, a square base, and a volume of 10 cubic feet. The base of the box costs $3 per square foot, and the sides cost $2 per square foot. Express the cost to make the box as a rational function of the width of the base. We have a width, a length, and a height. We know that this has to be square, so let's use x and x for the width and length. The height, I don't know what it is, but it does tell us the volume has to be 10. We also know that it has no top. And if you were to flatten all the sides, you would see the base, and then each side would be x by h, and there would be 4 of those. Okay, we know that the volume has to be 10, and the volume is also x times h. This tells me that h can be calculated by doing 10 divided by x squared. Now let's do the cost. We'll use cost as a function of the width of the base, because the width of the base we're using is x. So we have to do the cost of this one plus the cost of these sides. And the cost is $3 per square foot for the base, and these ones are all $2 per square foot. So we just got to figure out the area of the base and multiply it by $3 per square foot to get how much it costs. So the area of the base is x by x, and multiply that by 3. If I were to put units on this would be $3 per square foot, and x squared would be measured in square feet. So you can see that 3 times x squared gives us dollars. Plus, now let's just do one of these, but then multiply that by 4. So we'll have 4 times, and the price of this one here is $2 per square foot, and then times x times h, square feet. The other issue is that we have an h here. So we're going to use this volume restriction, it's called a constraint equation, to replace the h there, and that's how we're going to create our cost function. So our cost function is 3x squared plus, we have an 8xh, and h is 10 over x squared. So that gives me a cost function is equal to 3x squared plus 80 over x. If you wanted to, you could get a common denominator and write this as 3x cubed plus 80 all over x. And this is why this is a rational function. It's a polynomial divided by a polynomial. So we've answered part A. Part B is use technology to find the dimensions that minimize the cost to make the box. So we want to find x. Notice x has to be positive. It can't be 0 because then you would not have a volume possible. Right? You can't have 0 here. Has to be positive because it's a length. So that would be our implied domain. So let's go to Desmos and graph this, and then change my scale until I can see the graph. And also, I'm only interested in graphing this function for x being bigger than 0. So you could go in here and put in your curly brackets and then say that x is bigger than 0. Okay, now I change my vertical scale so you can see things a little bit better. Zoom in. We are clearly seeing that there is a choice of x I can make where the cost will be a minimum. Keep in mind that any point along this curve, then the first coordinate is what x should be, and the second coordinate is how much it would cost if you use that x. We want to minimize cost, so we want this minimum point right there. If x is 2.371, then the smallest possible cost will be 50.61, we'll say. So we have a curve that has a minimum. All right, so figure out what h is, which this says find the dimensions. So this is x. So this is this x here and this x here. So we know the dimensions of the base. They have to be 2.371 feet each. But then what does h have to be? We'll use this constraint equation. So let's do 10 divided by 2.371. That needs to be squared. So there's our h. That's x, that's cost. H is 1.779 rounded feet. X is 2.371 feet. This is both the length and the width. And then, of course, the min cost is this C coordinate, which is $50.61. And this wraps up graphing rational functions and also gives an example of a rational function showing up in application.